Hello, so welcome to this video. So in this video we're going to be talking about the motion of fluid across space-time, and we're going to therefore be discussing the energy momentum tensor. Now the energy momentum tensor is something you'll see all over the place in physics. I mean, it even comes up in general relativity because it describes the distribution of energy and matter, and therefore can allow us to kind of compactify how matter is distributed across space-time in such a way that we can then work out the curvature of space-time as a result of that matter and energy. So we're going to use the energy momentum tensor in general relativity, but I thought before we see it in the context of general relativity, it's worth firstly introducing it in the special relativity playlist. So this will be energy momentum tensor from the perspective of special relativity, where we'll be looking at the motion of large groups of particles, such as dusts within molecular clouds or planetary nebulae, or also kind of pushing it a bit further, we'll look at non-viscous fluids. Hello, so well, I suppose hello again. So we can now talk about kind of why we just can't use energy directly if we want to talk about the energy of a kind of fluid or collection of particles in special relativity. Well, there's a kind of key problem with talking about energy, and that problem is that energy is not a scalar in the context of Lorentz transformations, and by that I mean if we jump to a different Lorentz frame, the energy we would associate with something would change. And that's actually not too surprising, because that happens even in kind of non-relativistic physics. Because, for example, if at the moment my mug is stationary according to me, if I was going to get up from this chair and then run with a uniform velocity across the room, so go to a different Lorentz frame, the mug would no longer be stationary relative to me, because the displacement between me and my mug would change over time. And therefore I could say that in that reference frame, the mug would now actually have some kind of energy associated with it, which it didn't before. So the idea that kind of we can't really use energy as a good scalar, actually that's generically true. Like, special relativity complicates the problem of talking about the energy of dust moving, because usually when we talk about energy we consider, well, how quickly something's moving, and therefore we consider its velocity and therefore the distance it travels and how long it takes to travel. But we know from special relativity that quantities like distance and time taken are themselves relative. So the idea of using energy to describe something is fraught with complication and special relativity. So we don't really want to describe the distribution of energy or momentum of a kind of collection of particles by referring to energy and momentum distinctly. But thankfully, we know of a 4 vector which has energy and momentum in, and that 4 vector is a Lorentz invariant vector. It's a genuine vector within special relativity. And this vector is 4 momentum. Now, 4 momentum, the first component of 4 momentum is energy. When I say first, I mean P0. We're starting counting from 0. I don't know why we do this. I think it's a little confusing. Maybe it's because kind of like we've taken inspiration from American counting systems, where often you'll have things like the ground floor being 0, which constantly confuses me. Even in places in England, if I'm going somewhere and the ground floor is 0. Anyway, it all adds to the spice, I suppose, of things. But the first component of our kind of 4 vector the first component of 4 momentum is energy. And you might think, well, isn't it energy divided by the speed of light? Well, for this video, I'll be taking the speed of light to just be 1. And I'm doing that because by this point in the special relativity playlist, we have covered a lot of special relativity, and also I want to possibly reference this video when talking about particle physics at times, and definitely particle physicists always set the speed of light to be 1 because that just makes all of physics so much simpler. And there are also other reasons for doing that, such as here, if we're saying c is 1, we're also saying c doesn't have any units, and that's an indication that we're considering time and space on equal footing, like we do in special relativity. So there's lots of reasons to do that. But anyway, if we take c equals 1, then the first component of form momentum is energy. But what about the other components, our spatial components? Well, these components are just the momentum of something through space. So we've got a vector, a full vector, that is genuinely a vector and therefore good to use in special relativity. And this vector contains descriptions of the energy and the momentum of the particles that are moving. So that's a good place to begin. But when we say moving, how do we characterise their movement? Well, if they're moving through space-time, we can kind of imagine them moving through a 4-dimensional version of a cube, a kind of hypercube. Well, we can at least conceptually imagine it, even though we can't visualise a hypercube. But anyway, we've got our particles moving through the hypercube, and if we want to measure how much they move through it, we're really talking about their kind of divergence. Well, sort of their divergence, really more so their kind of flux across the walls of this hypercube. So if we were to talk about the motion of a group of particles in space-time, we'd want to talk about the flux of this form momentum across the different dimensions of space-time. So, that will describe us how much our fluid is kind of flowing through space-time. We're kind of imagining a hypercube and looking at kind of the flux of this form momentum vector across, the different surfaces of this hypercube. And this is fairly airy-fairy for now, so let's go on to exact, more kind of detail with looking at this flux and calculating components of it on the next part of this video. So we've talked about the idea that we really want to describe the flow of energy and also momentum through space-time using 4 momentum as a vector, and we also want to take the flux of 4 momentum across space-time. And if we choose fluxes along our different dimensions of space-time, we can consider the flow of energy and momentum of our kind of particles in our dust or fluid, and I'll go through the distinction of a dust and a fluid in a bit, but we can consider the motion of this energy and this momentum as the flux of 4 momentum in 4 position, because 4 position is marking our different directions of space-time. And because 4 momentum and 4 position are themselves vectors, and therefore have Lorentz invariance, even if their components do not, the energy momentum tensor that we get through looking at the flux of 4 momentum through 4 position will itself be a tensor. And so that brings us neatly on to the definition of the energy momentum tensor, which is exactly as I've described it, the flux of 4 momentum in the in the different directions of 4 position. Now, because 4 momentum has 4 components to consider, and we're looking at the flux of each of these 4 components in each of our 4 directions or 4 position, we're going to end up with a 4x4 matrix. So the energy momentum tensor, if we want to list its components, we'll list the components in a 4x4 matrix. Importantly, the energy momentum tensor itself is a Lorentz invariant. Its components, however, we only get when we pick a particular coordinate system. So the components of the energy momentum tensor are not necessarily Lorentz invariant. And we'll come on to that detail about the components when we relate the energy momentum tensor to forward velocity. But for now, if we're just sticking with for momentum and for position, let's have a go at calculating some of the components. And we don't really need to worry about the reference frame we're picking to find the components in yet. So we're still going to be working very generally. So the first component, the component on the top left-hand side, will be the T0 component. Now this is the flux of P0 in the x0 direction. Now P0 is energy, or relates to the energy of something, and x0 is time. So we're trying to find the flux of the energy of our dust or fluid across time. Now, it might be like, you might think, how on earth do we find fluxes across time? Well, we use the idea that the flux of, say, A in the direction B is given by the change in A divided by the change in, well, divided by the area where that area is perpendicular to B. So we have to ask ourselves, what is perpendicular to the x0 direction? Well, space-time is a four-dimensional structure, and three of those dimensions are perpendicular to time, and these are our spatial dimensions. Now, whereas usually if we're calculating flux in 3D space, our area will be two-dimensional, when we're dealing with flux in space-time, because space-time is four-dimensional, the flux will be three-dimensional. And if we're looking at fluxes relative to time, then the three dimensions we're going to consider is the dimensions of space. And that way we end up with T0 is essentially a infinitesimal amount of energy divided by an infinitesimal spatial volume. So it's the energy density. Now, when writing down the idea that the surface area, if you like, of space-time has to be perpendicular to time, if we're looking at the T0 component of our energy momentum tensor, I've used a symbol that engineers use and I absolutely love, which is a kind of like this symbol, upside down T, and it's just telling me that my space-time area has to be normal to time. But again, because space-time is four-dimensional, when I say area, I am going to be meaning a three-dimensional structure, which, confusingly, in this case would be what we usually call volume. It's not a volume in space-time, it'd be a spatial volume. So, as I say, T0 is the energy density. And an important thing to remember, which we're going to see, well, we're going to make use of later on, is for something that is not relativistic, the predominant amount of energy density will come from its mass density. Because for non-relativistic things, the rest mass energy far exceeds their kinetic energy. And therefore energy density is very approximately the mass density for non-relativistic stuff. And mass density usually has the symbol rho, so I'm using that here. Even though we also use rho for other densities such as charge densities in electromagnetism, And rho even has a relationship to densities associated with wave functions and things, which I won't really be going into in this video. But rho generally represents in physics density. Now, TII is the flux of PI in the xi direction. And when I'm using I really mean the index mu, where mu is 1, 2, 3, but not 0. So I is always referring to a spatial component of a vector. So PI is a spatial component of form momentum, so it's going to be form momentum across space, and XI is going to be a spatial dimension, so we're trying to find the flux of spatial momentum in a spatial direction. Now, a thing to note is because we're trying to find flux in a spatial direction, the area is going to consist of all dimensions which are perpendicular to that spatial direction. But because we're working in space-time, one of the directions that are always going to be perpendicular is time. And it's time, it's the fact that, one of the elements of our surface area is time that makes TII components rather distinct from T00. So TII would be essentially a infinitesimal spatial momentum in the spatial direction divided by a infinitesimal surface area, where that surface area consists of time and also the two spatial dimensions which are perpendicular to the ith direction. So, in the way I've wrote it, J and K are essentially the two spatial directions which are not along the ith spatial direction. And we can kind of rearrange this fraction a bit, even though mathematicians might not like me referring to infinitesimals here as relating to fractions, but we do it all the time in physics, and thankfully it tends to work. So dpi by dt we can group together, and I've done that because dpi is the change in momentum, dt is change in time, and from Newton's second law, you might be familiar, change in momentum over change in time is the force. So we have TII is the force divided by now a spatial area, so a two-dimensional area, so dxj, dxk. And remember, J and K are perpendicular to I, so this area is normal to the direction of the force. So TII is force divided by area, which is normal to the force. In other words, TII is simply the pressure on this spatial surface area. So this is the list of our kind of diagonal elements, and again, to just briefly emphasise, T00 looks from our perspective rather different to TII, because we distinguish between time and space, even though our equations in special relativity, in their fully covariant form, don't really differentiate between the two. And that's why, the energy momentum tensor is, in the context of special relativity, a single thing and very unified, even though we can break it down into a component referring to energy density and a component referring to pressure. But both of these components are fluxes of a full vector in the direction of another full vector. So in the context of space-time, they're fundamentally components describing the same thing. So before we were looking at diagonal terms, if we look at off-diagonal terms, and I'm really going to be sticking for now for off-diagonal terms relating to finding the flux along a spatial direction, well, because we have off-diagonal terms, our kind of surface of our space-time may now lie along the pressure, where the pressure is kind of a component in our energy momentum tensor. And so we're going to have pressure acting along the direction of the surface, and that's going to lead to essentially shearing. And shearing, essentially shearing then causes forces, well, shearing relates to forces which are not perpendicular to a surface, and when you've got forces which are, say, at an angle to a surface, if the surface can move, we start seeing the kind of like motion we do when we're dealing with fairly viscous liquids. I mean, if you've ever tried to like move your hands through honey, you'll see the honey doesn't just move it doesn't just move in the direction you're applying the force, it also moves parallel to the surface area of your hand. And generally these shearing forces are relating to intermolecular forces present in fluids, which is why if a fluid is very viscous, these off-diagonal terms of energy momentum tensor will be very important. However, we tend not to be looking at viscous fluids in the context of relativity, because usually if particles in a fluid are moving very quickly, then for them to be moving so quickly, they're kind of acting fairly independently of each other, and so generally we're dealing with things like gases, and gases have very, very low viscosity. So to a good approximation, at least in the context of special relativity, our energy momentum tensor can be considered as a diagonal matrix. So we've looked at the energy momentum tensor, we've discussed whether it can be diagonal, and we've done a fair bit of work on it. But now we're going to relate the energy momentum tensor to forward velocity. And the reason we're going to do that is we're going to want eventually to get to a conservation law that has forward velocity in it. Because it turns out if you treat the energy momentum tensor as being conserved, which Nether's theorem said it should be, then if you restate that, but in terms of forward velocity, you get to some familiar looking, fairly classical equations. And I thought it'd be neat to show how some classical physics emerges from this very relativistic, tensor. So we're going to relate energy momentum tensor to forward velocity. Now, up to now, I've been very kind of lucid, if you like, with both my reference frame and talking about dust and fluid. Here I'm going to start to be a lot more specific. So the first thing to know is if we are talking about dust, we are talking about a group of particles that isn't exerting any pressure. Or at least I can find a reference frame where there is no net pressure exerted by the dust. They do have energy density. And this can be useful. I mean, if we're looking at kind of like dust in deep space, they're not exerting. The dusts are quite spread out. They're not really exerting pressure on each other or on any surfaces. But the dust particles do have energy density. And if we recall, our energy momentum tensor, it's diagonal. Because we're assuming that our dust doesn't have any viscosity, so it's diagonal. And the first element is energy density, and we just said that for a dust, all the other elements along the diagonal are 0. So the energy momentum tensor for dust has a single non-zero component, which is the energy density of the dust. And we want to describe this component ideally in terms of form velocity. Well, here's how you do it. You consider kind of two vectors. First of them is form momentum, which we can write as the kind of mass multiplied by form velocity, and the other vector is a vector called n, and n is like something that has many names, but it's sometimes called the number flux for vector, and it's essentially the density of the kind of number density of our dust particles times form velocity. And I've wrote these out explicitly here. And m is just a scalar, n, the number density, is also a scalar. And because the first component of our energy momentum tensor for dust is mn, because that will be just, the number density times the mass density, which would be, the first component of energy momentum tensor for dust will be mn, where m is the mass of a single particle of dust, and n is the number density of our dust. We're going to get the kind of, we're going to get the mass density when we multiply them together. And if our dust isn't exerting any pressure and we're in a reference frame where our dust isn't moving, then the energy density is just the mass density of our dust. So the formula we've got for the relationship between the energy momentum tensor and form velocity is assuming we are in the rest frame essentially of our dust, so where there is no average motion, such that the energy density and the mass density are the same. Again, we're taking CT equal 1, so energy, so rest mass energy and mass are kind of equivalent. Now you might wonder, well, what about the, what about the other components of the energy momentum tensor for dust? Does our formula ensure they're 0? Well, if our dust particles aren't moving in a particular reference frame across space, then u mu is going to be 0 for everything apart from its first element. Meaning, although it might look like we should have lots of elements, realistically the only non-zero element for our energy momentum tensor is mn times u naught, and u naught is just 1, because we made the speed of light 1. So the energy momentum tensor only has one non-zero component, which is mn, which is the mass of a dust particle times the number density, which is going to equal the mass density, and because our dust isn't moving, that's equal to the energy density. So that's the kind of logic we have here. Now, for a fluid, we have something a little bit more elaborate for our energy momentum tensor. For a fluid, fluid is something that is entirely described by energy density and pressure. Now, for fluid, we therefore have essentially all of our diagonal components are going to, at least in principle, possibly be non-zero. So how do we get the other diagonal elements apart from the first one? Well, firstly, because, you know, our dust particles may now well be in motion, because there's some pressure associated with them, we can't say the first component is mass density necessarily, but we can say it's still energy density. But again, we could still, even if our dust is moving and therefore exerting pressure, we could still pick a reference frame where the average motion is 0. Now the pressure isn't necessarily 0 because the pressure is a scalar thing. So the average pressure doesn't necessarily average to 0, but the average velocity, as velocity is a vector, can average to 0. So in the reference frame where our fluid is, you know, overall the net kind of aspects of our fluid is overall stationary. U mu and U nu, essentially, these kind of components are going to be 0 apart from their first component. So U naught is 1, but Ui, where I is 1, 2, or 3, is going to be 0. So bearing that in mind, we can get essentially a matrix with energy density on the top and pressure along the rest of the diagonals by adding essentially pressure to our other diagonals, and that's what the second term is doing. P times the Minkowski metric is bringing P along the kind of diagonal, but the Minkowski metric, the first component of it, so at 0, 0, is -1 if we're using the convention for our metric of minus plus plus plus. So we have to add something to our first term for the energy momentum tensor, which will cancel the minus p to ensure the first term only has energy density in. So we have to add p to the first term in our energy momentum tensor expression, such that it will cancel out with the minus p we get from the second term. And so, you know, that's, I would encourage you to kind of show that for a reference frame where the kind of fluid is stationary, the energy momentum tensor for a fluid is a diagonal matrix, where the first element is the energy density and the other kind of diagonal elements are the pressures. Now small p is pressure and big P is kind of momentum. It's important not to get these things confused in this video. Now I have a kind of gone through showing it explicitly because I think it's good practice to look at a formula and try to understand how to break it down, but I would encourage you to try it out. So we talked about our energy momentum tensor. We've got an expression for the energy momentum tensor for our fluid, and we've expressed the energy momentum tensor in terms of form velocity within the reference frame where the fluid doesn't have any net motion. So we've done a lot of things, but you might wonder, well, you know, the energy momentum tensor, okay, it's kind of cool. It links energy density to pressure in some unified, relativistic, bizarre way, but how do we actually see this energy momentum tensor? What physically does it seem to do? Well, a key thing about the energy momentum tensor is that it is conserved, and just as with kind of the idea of charge and energy being conserved in an electrical circuit allows you to, you know, predict things like Kirchhoff's first law, And, you know, if you bring currents into the picture, you can get kick-off-second law. You know, just as the idea of charge being conserved is kind of a critical part of behaviour we can predict when we consider moving charges. Similarly, the way that we perceive the energy momentum tensor is really through the energy momentum tensor being something that is conserved. And the notion that it is conserved is something that we can thank Nether's theorem for. And Nether was a brilliant mathematician, and this image isn't quite drawn to scale. You know, she never took up the whole sky, but she definitely made a very firm contribution to physics. Essentially, Nether really, I mean, you can rephrase what she did in terms of group theory, but in the context of how physicists would tend to think of Nether's theorem, Nether's theorem essentially went, if you have some field and you've got a Lagrangian for the field, then Nether's theorem is a kind of algorithm you can do, a recipe if you like, which you can follow to find things that will be conserved about this field if its dynamics is governed by that particular Lagrangian. So if you have some way of deriving or postulating what a Lagrangian should be, you can predict things that should be conserved if the dynamics are genuinely described by that Lagrangian. So, you know, it's a really cool theorem, really. And it gets to the heart of physics, you know, conserved quantities. I apologise for a slight deviation there into field theory, but, you know, Nether's theorem pops up in so many places. And the energy momentum tensor itself pops up in so many places, and the kind of one of the most fundamental reasons for this is whilst we've been relating the energy momentum tensor to forward velocity, we've also seen we can relate it to for momentum and for position, and one might begin to wonder, well, can we relate it to anything that is even more fundamental, given it seems to be related to all these different force vectors? And we can, and the thing we can relate the energy momentum tensor to is the metric. And because all of physics, you know, ultimately relies on the metric, even if, you know, not explicitly, because, you know, all of physics fundamentally has elements of classical or relativistic physics ingrained into it, and both, you know, classical and relativistic, many elements of classical physics are Newtonian approximations of relativity, and relativity is all about the metric. So, you know, because our universe seems to be describable in terms of metrics, the energy momentum tensor is an important aspect of our universe. Now, the energy momentum tensor, as I mentioned, is conserved, and that means that the space-time derivative of it is zero. And importantly, the space-time derivative is a partial derivative that runs over all our dimensions of space-time. So the kind of key physics of energy momentum tensor is that it is conserved. But we need to ask, how does this conservation manifest? Because we don't see the energy momentum tensor. You know, you're not going to go to the shops and see something and go, ah yes, there is a 4x4 energy momentum tensor in space-time, because we don't really see space-time. We see space, and we feel time, if that's the right word, but we don't see space-time. However, thankfully, because of how we broke down the energy momentum tensor in terms of forward velocity, we can actually reinterpret this kind of conservation law in terms of forward velocity, and then break that down into time and space components. And that's what we're going to do now. So we start with kind of putting our space-time derivative in front of our two terms for our energy momentum tensor of a fluid in the rest frame where there is no net motion of the fluid. And I've been picking that rest frame because it's just fairly simple. because the energy momentum tensor is a tensor, the kind of physics will work no matter what rest frame we pick. But if we pick a reference frame where the where the fluid doesn't have any net motion, it just makes our terms a lot simpler. So that's a reference frame we're going to be using. Now here you might think, product rule, but before we do that, there's something to kind of quickly mention. So you get a similar kind of conservation law of energy momentum tensor in general relativity, but with the partial derivative replaced with the covariant derivative. But one complication you end up with that we don't have in this case is that in general relativity, your metric can vary over space-time, and that is a key thing, because it's that variation that at least permits, in principle, your space-time to be given. But we are dealing with flat space-time, and so on Minkowski metric, the components aren't changing. At least in Cartesian coordinates, the components aren't changing. And so we can just pull the Minkowski metric out of our second term, and we end up with this. And also in the second line, I've used the product rule to break up the terms in my first bracket. Well, break up the terms in front of my first space-time derivative. So we end up with this expression, and you might wonder, well, can we do anything more with it? Well, we can do a little bit more without really bringing in any tricks. And that little bit more we kind of do is just note that the Minkowski metric acting on a space-time derivative, because the space-time derivative essentially behaves as a kind of tensor, albeit a covariant vector in its own right, the metric can actually raise the index of our space-time derivative, and that's why we've gone from partial derivative in the mute direction to partial derivative in the newt direction. And because the index has risen, it's gone from being a kind of subscript to a superscript. And you might look at this bottom equation and go, oh my god, this equation looks really hard to interpret, and indeed it is. But we're going to now make some special tricks to simplify this quite dramatically, and then we'll get to something that is far easier to make physical sense of. So let's kind of get to a simpler expression. So we started on our last slide with the top expression, and using the using the product rule to expand the partial derivative of u mu, we get our bottom expression here. Now this bottom expression particularly looks incredibly bulky. We want to simplify it, and we see when you're simplifying things, you should always look for what is it in an equation that is making it look particularly complicated. Simplifying shouldn't be about necessarily just diminishing the number of terms. It should be about making sense of expressions which are hard to interpret. And there's kind of two expressions which kind of appear and are not particularly physically sensible. Well, don't make much physical sense intuitively anyway. The first one is what on earth u mu is, The second is what on earth is u nu times the space-time derivative of u mu? You know, like, what are these kind of terms where we have these two full velocities, or a full velocity multiplied by a derivative of another full velocity? And so we want to kind of look at those and see if we can use any tricks to simplify those terms. We kind of are close to doing it, but not really. We're not really there quite yet. And the reason we're not really there quite yet is there are certain things we can make sense of, but making sense of u nu, because there's no relationship between mu and u, that's not something we can really simplify. We can, however, simplify it if we essentially contract all of our terms with the u nu, where nu is on the bottom, because then we'll get a scalar product, and we'll get u nu with u on the bottom times u nu with u on the top. And the scalar product between two 4 vectors is, you know, something we've looked at before, and we've seen that the scalar product between, well, the scalar product of 4 velocity with itself is -1, if we take the speed of light to be 1, which I am doing for this video. And so, you know, when we're contracting, we'll have an important relationship that u nu times u nu is -1, but we'll also kind of have, because we're contracting with u nu with nu on the bottom, we'll have u nu with nu on the bottom next to our partial derivative in terms of mu of u nu. You know, using the product rule, we can say that is equal to 1/2 times the partial derivative of mu of u nu, where one of the u's is on the bottom and one is on the top. And because u nu is a scalar product, which is -1, the partial derivative of -1 is 0, because -1 is a constant, it doesn't change across space-time, it's just a number. And therefore, we can say that u nu times partial derivative in terms of mu of u nu is going to have to be 0. And then, essentially, so if we contract with the u nu, we initially get this really complicated expression, but then using our key mathematical details, we can simplify it dramatically. So immediately it simplifies to this expression, and then what we can do is we can simplify it a little bit more. So when we're simplifying it a little bit more, we're just kind of cancelling out a term we get from adding so our last term at the end will essentially cancel out with one term we'll get from the middle. And then that leaves us with just 2 terms which are equal to 0, and then if we kind of think about the product rule, our bottom equation on the left is the same as the bottom equation on our right. And you can check that by expanding the bottom equation on our right using the product rule and see that it gives you the bottom equation on the left. Now, I've gone through this fairly quickly because there's a lot of algebra and there's a lot of symbols, but fundamentally all we're doing is we're contracting with u nu when u is on the bottom, and then we're using our key mathematical details to simplify our expression, and then using the product rule to write it even neater at the end. Now I haven't, in words, kind of spelled out, all of the algebraic simplification, because it'd be a bit of a tongue twister saying mu and nu all the time. I'm already having to be very careful when I do use them. Personally, I feel we should ditch sometimes using Greek and use Elvish instead, because I must say, having an alphabet where we don't have two letters that sound so similar would make my job just so much easier. But I guess it's a brilliant opportunity for rappers and people showing their flair with pronunciation to make cool video and songs out of. So if you're watching this and want to really impress everyone with distinguishing between mu and you really rapidly, maybe make a rap and make physics even more kind of like accessible, and expose it to loads of people. I mean, I'll always be up for a rap on the energy momentum tensor, but then I feel like I'm probably not the one to do it. So we've talked a lot about the energy momentum tensor, and we've got an expression for the energy momentum tensor conservation in terms of forward velocity, and this is a covariant equation, and so will be valid in all reference frames, no matter what reference frame we picked to derive it. And so we have this equation. Now, when deriving this equation, we looked at the components of the energy momentum tensor in the rest frame of the fluid, so where there is no net motion of the fluid around us. But because it's a tensor equation, this equation is guaranteed to work if we were to jump to a different reference frame where our fluid does have motion, potentially. And if our fluid does have some net spatial motion, then the components of u are for velocity. All of the components could be non-zero. So the time-like components is bound to be non-zero. But if our fluid has net motion, the space-like components will also be non-zero. So recalling that u, in terms of its components, is 1, spatial velocity component, so small v, when not used as an index, represents a spatial velocity vector, and vi is the component of that vector along the spatial axis. And if we substitute our expression for u into our top equation and break down our space-time derivative into a time derivative, so a partial derivative in time, and its spatial part, which will be the divergence in space, we end up with this equation. Now this equation has got 3 terms, all of which have a fairly natural physical interpretation. So the first term is clearly the rate of change of energy density, and in non-relativistic settings, energy density is predominantly mass density, so the first term would be very approximately the rate of change of matter density. The second term, well, again, if we're considering non-relativistic situations, the energy density is approximately the mass density, which is mass divided by volume. So our second term becomes the divergence of mass times velocity divided by volume, or in other words, the divergence of the momentum density. And our third term, well, for our third term we look at the units, and we can see that our third term is equivalent to the power density, or the rate of transfer of energy per unit volume. Now, this third term is only present if the pressure of our fluid is non-zero, so we can think of this third term as the rate of energy transfer per unit volume due to the pressure of our fluid. And so here is kind of the summary of our three terms. Now this is really a kind of conservation equation, really. And we you know, we can kind of see that in some ways, because kind of like if we're considering that, say, a non-relativistic fluid, and this non-relativistic fluid is in a box, and let's say, it's trapped in this box, so there's no change in the mass of our fluid, and let's look at the non-relativistic case. So there's no change in the mass of our fluid. Then our equation is saying that essentially the second term in the bottom equation, three terms, the second term must be equal to minus the third term. And the second term is the momentum density, and the third term is kind of like a change in energy density due to pressure, and we would kind of expect that the kind of divergence of momentum should be related to energy density of our fluid. So there's a fairly natural physical interpretation. If you would like to look into more detail at our continuity equation, so our equation with the three terms set to zero, I would encourage you to look at the Navier-Stokes theorem, which does make use of this idea. So we have brought the kind of conservation of our energy momentum tensor into an equation which is a lot more kind of familiar, and is actually one of the founding equations when describing the dynamics of fluids, such as in Stokes' law. And Stokes' law, in principle, describes non-relativistic fluids quite generally, and therefore describes everything from cyclones to the pouring of water and many things. Now you might wonder, we have as our final classical equation an equation in terms of divergence, but we began with the definition of the energy momentum tensor in terms of flux, and is there a relationship between flux and divergence, and indeed that is, and this relationship is known as a divergence theorem. And the divergence theorem, as well as relating divergence to flux, ultimately allows us to relate operations involving derivatives, like divergences, to operations involving directly integrals like fluxes. So the divergence theorem says that if we have a vector field V, then the divergence of a vector field integrated over the volume of an object is equal to essentially a closed integral of the flux of a vector V, along some normal surface area A. Well, across, I should say, some normal surface area A. So here, it might seem a bit magic, we made fluxes turn into divergences, but there is a theorem saying that the two are related. And part of the skill of a physicist is being able to turn one equation into an equation that looks completely different, but is perhaps more physically interpretable. So that's everything for this video. I hope this video has given you some intuition for what the energy momentum tensor is, and how we can go from relativistic equations to kind of more classical laws. And if you've enjoyed this video, consider kind of sharing it, because the universe is filled with many wonders, and the more people get to see the many wonders in the universe, the better, really. Well, I hope you kind of enjoyed this video, got something out of it, and have a wonderful day ahead, and may the flux ever be with you.